In these circuits, the voltage drop at each point of resistance are additive, and when totaled are equal to the applied voltage. So, if I have 4 resistors in the circuit, if this one was 3, this one was 3, this one was 3, and this one was 3, a voltage drop. Essentially, what does that mean? At every resistance, everything that has resistance, we're losing voltage because of that resistance. If we have a long wire span, we're going to be losing voltage because of the long length of wire. If we have resistance, can also be a light, could be a filament light. That's a resistance. We're going to be losing voltage on whatever circuits that we have. If you guys get tired, because I know some of you guys work graveyard, you can stand up, you can walk around. If you need to take a walk around the building, that's okay too. I know how difficult it is to work a graveyard shift. So we're losing 3 volts at each of these resistors. These are additive, so we got 3 and 6, we got 9, we got 12. So this is a 12-volt battery. And if we had attached a 12-volt battery to 4 resistors, we would have essentially would lose voltage at each one of these. Now, I just kind of made these up. If we started up at 12, we're going to lose 12 volts here. So if we started with a 12-volt battery, we might be losing 1 here. We don't know what the resistance of this resistor is yet. We might be losing 1, might be losing 6, we might be losing 4, and we might be losing 1 again.
I got a question for you.
Sure.
If the wire's got a long run and it loses voltage, can you put a heavier gauge wire in there and keep the same voltage?
You could put a heavier gauge wire and reduce the amount of voltage drop on the conductor.
I heard that before.
Yeah. Typically, when you get over 100 feet, you upsize the wire. Now, your tunnel is what, 5,000 feet? That's so what you're doing, and on particular cases for your facility, you're using higher voltage to take it down to as far as you can get. You got 480 volts, and you're using larger size conductors. You have, I looked on your plans, it showed 10 American wire gauge, at least on that set, going down your tube or your tunnel. And what is your load? You might have a 5 amp load that you're feeding with the 10 amp wire. 10 amp wire is good for 30 amps. So you're putting 5 amps on it. So you've upsized your wire quite a bit. But you probably, because of the long distance, you probably still are going to have confined voltage drop issues during your career.
Now, would that cause failure to some electric components? Let's say motion sensor lights?
Probably not motion sensor lights. You're probably going to see more failures with
those
motors.
light things that we have to trick?
Photocells.
The what?
Photocell?
Photocells.
You're probably not going to see failures in photocells because, well, you got to take a look at what voltage you have at that location. So if this photocell is 500 feet from here, what is your voltage at that location? Did you start off with 120 and you ended up with 80? Then yeah, you got an issue. You don't want to lose more than 5%, and this is kind of off topic, but you don't want to lose more than 5% than what you would have at your service. And it's broken down in components of 3 and 2. So you can have from your first panel to all your power distribution can be 3% or 2. And then from your last panel to the end of your load, it can be 2% or 3%. But whatever, however, you can't exceed more than 3 on either. But they can't total more than 5%. So if you started with 120 volts and you multiplied that by, or you figured out what 5% of 120 volts was, you can't go less than that, which would be 112 somewhere around there. So you don't want to go less than 112 volts if you started with 115. Good question. All right, so we're losing voltage drop at each point of resistance, and they're additive. When total, they're equal to the applied voltage. So that's our voltage. That's our green. You can see that in the green line up top. when it talks about voltage, it says voltage there. If we look in the back, voltage is in green as well. So it's color-coded to make it a little bit easier. The next rule for series circuits, it says the individual resistances are additive. So our voltages were additive, and our resistances are additive. So if this was, let's say this is our 1 ohm of resistance, this is 6, and this is also 4, and this is also 1. So our total ohms of resistance, our total ohms of resistance would be our RT would be 12, because it adds up to 12. The total amps is used as consistent throughout the circuit. If we had 1 amp being used here on a series circuit, we would have 1 amp here, 1 amp here, 1 amp here, 1 amp here. Everywhere on the circuit you would have 1 amp on a series circuit. Most of the circuits we use are going to be parallel circuits, but some of the circuits that you guys are going to be exposed to are going to be series. And when you work on one of those circuits, your ampacity is in parallel. It's consistent. Watt is used at each point of resistance is additive to the total sum of wattage. So whatever our watts, so our watts total is going to be our watts here, our watts here, our watts here, and our watts here additive, just like volts and resistance was. Those are the 4 rules to a series circuits. It's not very complicated. It's actually quite easy. It's just something you probably haven't been exposed to. So let's practice working with this information and see if we can apply it. So go ahead and flip over your first page, and you're going to see that on top of the second page, you're going to see that series circuit that I drew up here. You're also going to see a couple circles. One says ear and one says pi. Or I guess you'd say it says ear and pi. So I'll just draw them real quickly so I can describe them a little bit. Alright, can you see this okay, John?
Yeah.
Alright, good.
I got a paper too.
Great. So the first one on your left says ear, or EAR. This is your, E is your volts, A is your amps, R is your resistance. Just like the paper shows, and just kind of like how we kind of define that they're all essentially the same thing. If we're trying to solve for our volts, which is our E, we can cover this with our hand or with our thumb on your paper, and then we're going to take A and R. So we're essentially going amps times your resistance is equal to your E. If we're trying to solve for your ampacity, we can just cover the A, and we have our voltage divided by our resistance. Does that make sense? Yeah? You got it. Alright, now the same thing with power. If we're trying to solve for power, we're going to have our amps. See, and look what I did here. We have amps with an A, and we have amps with an I. The reason why I did this is because you guys can probably remember ear pi, but if I put an A there, you're going to be, I mean, it's not as easy to memorize. But anyways, our power is equal to our amps times our volts, so we'll cover our power, multiply the 2, and that's going to give us our power. If we're trying to solve for our volts, and we have our amps and our power, we can cover the E divided power by I, and we'll be able to solve for that equation. You guys have any questions on this before I erase it? You do have it on your sheet. I'm just going to need the space. Alright. So let's work through this. Our RT, so this is our totals. Let's call this T. So we have watts, we have our volts, we have our amps, and we have our ohms. And let's do this. R1, and we'll go volts, amps, and then we'll go ohms, R2, volts, amps, ohms, R3, volts, amps, ohms, and R4, volts, amps, ohms. Alright, so we have some of the information already here given on our sheet. It's in red. Why don't you guys read me what we have here for R1. R1 we have 72 ohms. So we know, and we would solve this stuff in several different ways. If we're in the field, we're using our tester, we're checking, hey, this resistor has a certain amount of ohms. So we could get some of these values in the field with our resistor. These are possibly where this information is coming from. So we got 72 ohms. Okay, do we have any information for R2? Oh, there's a typo. Let me explain that. So the second R3 on your right hand side should say R2. And our volts, we know what our voltage is on R2. That is 12 volts. You guys all see that? So R3, what do we know for R3?
0.5 amps.
Yeah, 0.5 amps. And you said 48 ohms?
48 ohms.
48 ohms. Alright, what about R4?
48 volts.
Huh?
48 volts.
48 volts. And anything else we know? Alright. So, how does this information help us? What would be our next step if we're trying to solve for all of these values to ultimately get to our total?
So for stick in any formula.
Okay, where would we start?
Well, you know what ohms is, right? So R is 72, right?
Where?
On the
R1?
Yeah.
Okay. So we know it's 72 ohms, and then what?
We gotta solve for everyone's what volts.
Okay.
So how do you get volts?
I'm asking you.
Pi.
R.
Huh?
Pi.
Our amp stays the same all the way through.
Divide it.
Who said that?
Amps.
Amps is the same all the way through?
That's what I thought.
Yeah.
Okay, so that's one of the rules. Amps is consistent everywhere. So if we have amps on R3 at 0.5, then that means right here we have half an amp going through this resistor. We have half an amp going here. There's no other path for the current to travel. So if we have half an amp here, we're going to have half an amp here, half an amp here, half an amp here, half an amp here. We're all on the same page? So what does that tell us? It means we could put 0.5 in every location. And now our problem becomes ultimately a lot easier. What Castle was saying, we solve for voltage. Now we know a 0.5 and 72 ohms. So what is our voltage here? I guess mainly your calculator or your smartphone or a piece of paper. Just pencil this out.
So you take the amps and the ohms, multiply that, and then divide by volts, right? We don't know what the volt is.
You guys tell me, what's our voltage?
So we have 12 and 48.
So you have, well, what's the voltage drop at R1? Let's solve for R1. You guys see the wheel? So you have the EAR, we cover the E.
36.
36. How did you come to 36?
72 times 0.5.
72 times 0.5. So he took the E, covered it with his finger, multiplied the A times the R, and he got 36, you said?
Yeah.
There you go.
Series, what is it? No.
Alright, so that's as hard as it is. This is very important for you guys to be able to do this, because you're, like I said, you're not going to be able to troubleshoot if you don't understand these concepts. So what about R2? On R2, all we need to do is solve for our total ohms, or ohms for R2. So this is still the AIR, the ear.
So divided by 0.5.
12 divided by 0.5 would be
24.
24. So he took our voltage divided by our ampacity and came up with 24 ohms of resistance. You guys all see how that happened? Is that what you got, John?
Yeah.
Okay. R3, resistor 3. We have 0.5 amps, we have 48 ohms of resistance. What's our voltage? I guess the important thing is to know is what's our formula? Ruben, you know what our formula is for R3? No? It's at the top of your pages.
Fall asleep.
What do you think? R times A? So R times A would be? So we're multiplying 0.5 with 48, because that's our I is our ohms. I'm sorry, our I is our amps, and our R is our ohms. So 48 times 0.5 is equal to 24. 24 volts. Good, you guys are. I put that too high, didn't I? 48. Alright, so our last resistor, we have 48 volts, we have half an amp. What's our resistance of this resistor?
96.
So you took 48 divided by 0.5 and you came up with 96. Alright, so very good. We solved for all of our resistors. We have 36 voltage drops, or volts dropping from R1, we have 12 from R2. This is how many voltage or volts we have dropping on each of our resistors. So how do we solve for our total voltage? We're just adding them all together, right? What does 36, 12, 24, and 48 add up to?
Come on, man. Let's see, you got 96 right there, 96 and
120.
14 or
Who said that? 120?
The phone did.
The phone said that? 120 volts. So they all added up to 120 volts. Our amps are consistent throughout our entire circuit. What about our resistance? How do we solve for our resistance?
Same thing, add them up.
We're adding them all up, all the resistors. We're adding them all up, which comes up to
72 plus 20.
240. So what if we, for some reason, we wanted to check ourselves, or maybe we thought one of these values were incorrect. We could go back just up here. We could have volts, we have amps. We wanted to solve for ohms. We could take 120 volts divided by 0.5 amps. That is equal to 240 ohms. So we know that we just double checked our formula here to know that all of this is correct. Now we have one more formula to do. Solve for our watts. This is the black. It's also our P or VA. So how do we solve for that? It's the circle on your right hand side.
Amps and volts.
Your amps times your volts. So we have 120 volts. We have 0.5 amps. That is equal to 60. John says 60.
This is a dividing line.
60
So it would be like this.
watts.
It would be
You guys, how do you feel? How comfortable do you feel
E
with this?
divided
You think you got it?
by E divided by
Okay.
I
Where?
get confused with the wheel, man. It's turn.
The
Which,
wheels.
which one at a time? Which one to multiply it
these two
from?
values.
But it makes
So
sense.
for here, you just
Is it because of the lettering?
Just the
or-
lettering.
Okay.
You know, it makes it easy
I got a
if
question.
you kind of,
Is your-
kind of label where your ohms are. You know, instead of, trying to figure out that the resistance is the ohms, that should be already be on there. That's,
Okay.
make sure that the, your watts and your power, you kind of label them the same so that people don't get more thrown out.
That's a good point. So, I'm sorry, your name was
Jaime.
Jaime. That's right. So Jaime says that he penciled in like what the power was. He said it was watts. He said the E was voltage. He said the I was. He just penciled it in next to these numbers. Next time I print this out, I think I'll make that change. I have this memorized, so for me
Yeah, you gotta
it
be
makes
into Ohm's
sense.
law and know.
But for you guys who aren't familiar with it, I can see how that might be a little confusing.
I got one.
Morning.
How you doing?
Good.
We're
Morning,
back.
guys.
Pat, what's up?
How you doing?
You ready for the barbecue?
I had to leave a little bit. Yeah. Barbecue sounds good, though.
Yeah, next time.
Yeah. So you get double duty, huh? Not the barbecue, I mean this.
Yeah. I was hoping to barbecue. I'm at it.
So sorry, guys, for
So, all right. So how comfortable do you think how comfortable do you guys feel with series circuits now? Good. So, John.
I'm okay.
Okay.
I got one question though.
Yeah.
On your, I could probably sit here and figure out. So watts is 1/4 of our ohms. Is that going to be?
Don't read
do
into that.
All right.
It's watts is watts is a product of our ampacity and our voltage.
Okay.
Now there are other formulas. If we had just our ohms and our voltage, where's that? Okay. There's other formulas. What is called the big wheel. You can use the big wheel. So you guys have the two small wheels on your sheet. There's something called the big wheel that uses a lot of other formulas, but they're very confusing. Well, they're not confusing, but you need a calculator to use them. And because you guys can use scratch paper and you can memorize these two, that's why I'm using only these two, because you can do exactly the same thing without having to get complicated with the big wheel. So yeah, don't read into that. How do you feel with these series circuits, David? How do you feel with series circuits? All right. How do you feel? So. Ruben? Ruben, right?
Yeah,
Okay. How do you feel with series circuits?
I don't.
You don't feel them. Castle? All right. So we have some that might be still a little hesitant. So what do you think might be holding you back? Is it the terminology that we're using, or?
Yeah.
Okay. So the important thing is to just think about each value in and of itself, and then refer back to the previous page. When we talk about series circuits, parallel circuits, we're going to use this. We're not going to use any new terminology. We're going to use the same terminology. Just the rules have changed. So these rules are only true for series circuits. All right. So let's change this.
You need to put some goats in there. You probably don't know about that.
Goats?
The goats got out last night.
Oh, did
So
they?
I liked your email this morning. So.
You had a little problem last night, Angelo?
Yeah, sure. Ruben handled it fine.
Frank was here. He'd been all over
Thank
that.
you, Lord.
Alright.
Hey, good thing you weren't chickens, huh? You really had a tough time.
So someone ended up being a goat roper last night?
Yeah, a goat roper. Is that what it is, you say?
That's a goat herder.
Alright, let's see. Erase this one.
Yeah, one guy down the tunnel.
Alright, so let's look at our rules. We're back at the page with the text on it. So like I said, the rules have changed for parallel circuits. So the one thing that makes it difficult when you're trying to troubleshoot a circuit is if you have a series circuit or a parallel circuit and then it fails in some ways, it could become a parallel circuit or it could become a series circuit because the circuit failed. If this goes to ground or if there is a resistance, something happened on this conductor, essentially this resistance or whatever happens here is going to be in series with these. So, and when that happens, the reason why it makes it difficult is because to troubleshoot is because our rules have changed now. We're not doing parallel, now we're doing series. And from the last one you guys just looked at, we did series, now we're doing parallel. Alright, so let's start off with the rules. A circuit that has all the loads connected in parallel. So each one of these resistors is a load. They're all connected in parallel. Just it's typical to, let's say, lighting, for example. Each one of these could potentially be a light fixture. The voltage in parallel circuits is consistent throughout the circuit. So if we were applying 120 volts here, that means that everywhere along this wire would be 120 volts. A potential difference, I said I was going to use that word, from here to here. So this wire is 120 volts of a potential difference everywhere along the whole span. Does that make sense?
120, 120.
Yeah, just if I have a tester, if I use my meter anywhere on this circuit,
I didn't ask you guys, do you all have a meter like that?
No.
No?
anywhere along this circuit, I'll have 120 volts if I'm applying 120 volts and the circuit is operating properly.
Vice
What?
versa.
Well, yeah, if I go from here to here, yeah.
Unless you go across the load, right? You go across the load.
Well, I still have 120 volts from here to here. So if I go from here to here, how many volts am I going to have? 120. What if I go from here to here?
120.
Ah,
Yeah.
who said zero first? Jez? So I'm testing the same wire now. There is no load in between the two conductors that I'm testing. If I'm testing the same circuit or the same wire, there's no difference. What about if I'm testing up here on this wire? This was the power coming out, right? Zero. So this is zero, this is where I'm testing the same wire. So if I test the same wire, unless there's a really long distance between the two, it should be zero. Now there are things that might change that. If, like I said, if there was a really long distance, then I'm going to be testing the voltage drop in that conductor. So if I have two wires to go start from here, go all the way to the end of the tunnel, and both of them go all the way to the end of the tunnel. On that end, I wire them together, so I have essentially 1,000 feet of wire for the whole circle. And on this side, I have the two. I'm testing the two to see if I have a potential. Let's say I apply voltage to one, and I test the two together. I'm going to see difference in potential between the two because I've lost voltage along that span. All right. So that's a parallel circuit. Our voltage is consistent through all of our loads. What's our next rule? The amps in parallel circuits are additive to the total amps. In the series circuits, if we had half an amp here, and half an amp through all of them, on a parallel circuits, they're additive. So if I have 1 amp here, 2 amps here, and 3 amps here, my total amps would be
6.
6. 1 plus 2 plus 3 is 6. So our total amps would be 6. So it's additive. Let's see. The circuit has more than one path for the current to return back to the source. So the current could go this way, or it could go that way, or it could go that way. So in this particular circuit, there are 3 paths back to the source. In a lighting circuit, every single light is going to be a path back to the source. If I have 50 lights on one circuit, I have 50 paths back to the source. Let's see, circuit has more than one path. Wattage used at each point of resistance is additive. So our wattage on a series circuit was additive. Our wattage on a parallel circuit is also additive. So that rule hasn't changed.
What's that mean? What's additive?
It means for every resistance, at every point of load or of resistance,
You add them up.
we're going to add them all up to achieve our total wattage. And same thing for the for every time we've used the term additive today. Let's see.
Some paint on that, right?
Due to many paths for current to flow, the total resistance is always less than the lowest resistor. Does that sound confusing? So if this had, we talked about ohms, if this had 1 ohm of resistance, this had 2 ohm of resistance, this one had 5 ohms of resistance, the total resistance of the circuit would be less than this one. The reason for that, and this is the tricky thing, it's hard for people to understand, the reason for that is because I have current traveling in this path, I have current traveling in this path, and I have current traveling in this path. So Ruben said earlier, if we increase the size of our wire, could we diminish voltage drop? Well, in some cases what we do is we put parallel conductors. So we have, I have this wire going out there, maybe I have 12 number 10s going out 600 feet. Well, that conduit's full. I can't make a bigger wire, pull a bigger wire through that conduit. So we can't eliminate our voltage drop that way. But what I can do is I can take 2 of those number 10s, wiring at them on this side, wiring at them on that side, and essentially I've made 2 wires into 1 because they're bonded on both ends. So whenever we add a particular path, a path or a new path for the current to travel, we're reducing our resistance. So our total resistance in this circuit would be somewhere less than 1. It'd be, I don't know, maybe half, 0.5. I don't know what it would be. We'd have to do a formula to figure that out. But we haven't gotten to that point yet. The total resistance for equal resistors is the value. Okay, so this is the total resistance for equal resistors is the resistor value divided by the number of resistors in the circuit. For this example, let's say if this was 9 amps or 9 ohms, this was 9 ohm and this was 9 ohm. Each one of these light fixtures have the same amount of resistance in them. They're all 9 ohms. Our total resistance for the circuit would be 9 divided by 3 is what that rule is telling us. So our total ohms would be 3 in this case. So we have 9, they're all the same, we're dividing them by 3. 3 is less than 9, so we've gone down. For circuits with 2 resistors, if you only have 2 resistors, let's say we'll just eliminate this one. We just had a 4 and a 5 here. If for total resistance of equal resistors, so let's see, for circuits with 2 resistors, you multiply the product of the 2 resistors and then divide by the sum. So you multiply them both together, and then you divide it by 4 plus 5. So this formula we don't use very often because, again, we're going back to the calculator. The last formula is if there are more than 2 resistors and the resistors are not equal, you must use the reciprocal formula. This is taking us back to when we had like 3 resistors, none of them are the same. We're basically going to take 1, divide 1 by 4, then divide 1 by 5, and divide 1 by 3, add all those up together, and then divide 1 by whatever that ended up being. So that, we don't do that in our head. We do that on our calculator as well. So I don't like to work hard. I'm not going to do any of those. What I'm going to do is I'm just going to solve for our other values, and then that way it'll be a lot easier. And I'll show you how to do that when we get started on the next page. Let's do that now. So we have. All right. So what do we know on our second page here? What do we know about this circuit? What do we have in red on R1?
120 volts.
So our voltage is 120. What else do we know? Anything on R1?
Oh,
60 ohms.
We have 60 ohms of resistance. What about R2?
60 ohms.
80.
60 ohms on R2? 80 ohms on R2? Okay, R3?
120.
Well, what?
Oh.
120 ohms. So we can do that reciprocal formula to figure out what our total ohms is, but I don't want to do that because that sounds like a lot of work for me, or for you also. What else can we do with the circuit?
We can put the volts in. The volts are the same, right?
John says the volts are the same. At R1, which is right here, R3, the voltage at R1 from here to here is 120 volts. And we know that whatever voltage is from here to here on this load is going to be the same for all